Hey everybody, welcome to Pre-Calculus Unit 8. We are here at the beginning of a new unit which is all about polar coordinates and polar graphing systems. So we're going to start off here in Lesson 1 with plotting points using polar coordinates. So as a little bit of background, by now you are familiar with lots of different types of graphs. So you can look at something like this first one and say, oh yeah, that's a linear equation. It's going to have the form y equals mx plus b. Or you can look at this one and say, oh yeah, that shape is a parabola. It's going to have an x squared term in it. You probably also can recognize cubics, absolute values, exponentials, logarithms, or more recently from pre-calculus, the graphs of the sine, cosine, and tangent functions. So these all have different equations of the form y equals some function of x, whether that's y equals 1 over x, or y equals the tangent of x, or y equals square root of x, what have you. But for all of these, they have some sort of recognizable pattern that allows you to identify it as being a cubic function or a square root function. You can tell that these are not just random scribbles that somebody drew on a page. They have patterns and they have recognizable and predictable values. So these are all functions that can be written as the form y equals f of x, like I said. You also probably could recognize some conic sections. So things like the graph of a circle, where you have x minus h squared plus y minus k squared equal to the radius squared. So these are not functions. They fail the vertical line test. If I draw a vertical line through here, it crosses the graph in two different spots. But we can still represent them in terms of x and y variables. These still have a recognizable pattern that you have learned how to identify and then manipulate. What about graphs like these? I see a circle, I see kind of a figure 8 shape, I see some that kind of look like flowers, I see one that looks like a spiral. And these are obviously not random shapes. They are shapes that have a pattern, a symmetry, kind of a beauty to them. These are kind of fun or pretty shapes. But how in the world would you write an equation for a graph like that? Obviously, they have some kind of a pattern. It's not random. So there should be some way to represent that pattern mathematically, but it's no way that you have ever seen before, most likely. So what we are doing here is we are going to introduce a whole new system of graphing things that is based on a circular pattern instead of a square or rectangular pattern. And that's going to give us a lot more flexibility to graph types of shapes that you couldn't easily represent before. And that is called polar coordinates. So polar coordinates are a two-dimensional coordinate system, so you can draw it on a flat piece of paper, in which each point is defined by its distance from the origin and its angle from the positive x-axis. So distance from the origin and its angle from the positive x-axis. So when you see an ordered pair in polar coordinates, you'll be thinking of that in terms of r and theta instead of x and y. So you're used to seeing an ordered pair that's something like 1, 2, and that tells you to go to the right 1 unit and then up 2 units to find your point. In polar coordinates, if you see 1, 2, that tells you to go 1 unit away from the center and then wrap around an angle of 2 radians. So r is the radius or distance from the origin, and theta, T-H-E-T-A, that Greek letter, that's used to represent the angle from the x-axis. So how do we graph these? If everything is positive, it's pretty easy to do. You just go a certain distance away from the center and then wrap around the angle that you're given. What if theta is negative? In that case, remember coterminal angles. Those are angles with the same terminal point, angles that end in the same place, but different angle measures. And those are found by adding or subtracting 360 degrees or 2 pi. So if you are trying to plot a point that has a negative angle measure, then you would add 360 degrees or 2 pi until you get a positive version that you can easily plot. And what if the radius is negative? Well, r represents the distance away from the origin. It's the distance traveled towards the given angle direction. So if r is negative, then the distance is going to be counted in the opposite direction. So you'd be going away from the given angle instead of towards it. So what does all this look like in practicality? We're going to start here with some very simple polar points. So when we're graphing each of these, you remember that the two parts of the coordinate system represent the radius and the angle, so r and theta. So this first one, I am given a radius of 2 and an angle of 3 pi over 4. So that means that I'm going to start at the center and go 2 units away from the origin. So I'm going to be on this second circle here at an angle of 3 pi over 4. So that is right there. So I'm going to be going 2 units away from the origin towards the angle 3 pi over 4. And there's the point that I would plot. If I'm looking for 6 comma pi, I'm going to be having a radius of 6 at an angle of pi radians. So that means I'm going to be going towards the angle or the direction of pi. And I'm going to be going 1, 2, 3, 4, 5, 6 units away from the origin. That right there is the point 6 comma theta. If I wanted to graph 1 comma 17 pi over 12, that means that I'm going towards the angle 17 pi over 12, and I am going a radius or a distance of 1 unit in that direction. So that would be the point 1 comma 17 pi over 12. So those were all positive angles. What if you have a negative angle? I don't see here on my grid paper anything that is negative. All of my angles are between 0 and 2 pi. They're between 0 and 360 degrees. So if you're given a negative angle measure, you have to find a coterminal angle that is positive. So you would take that angle and add 2 pi to it. So in this case, the angle is negative 2 pi over 3. If we want to add 2 pi to that, that's 2 pi over 1, so we need common denominators. So I'm going to multiply this by 3, and I would end up with negative 2 pi over 3 plus 6 pi over 3, and negative 2 plus 6 is equal to 4 pi over 3. So this point 5 comma negative 2 pi over 3 is equivalent to 5 comma 4 pi over 3. And 4 pi over 3 is an angle that I should be able to find on my grid here. 4 pi over 3, sure enough, it's right down there. So I'm going to be going in the direction 4 pi over 3, and I have a radius or a distance of 5. So I would start at the origin and go 1, 2, 3, 4, 5. There's my point. 5 units away from the center at an angle of 4 pi over 3. Another example where the angle is negative, I've got an angle of negative 7 pi over 4. Again, anytime you have a negative angle, the first thing you would do is add 2 pi to that. So you have one full revolution around the circle. And that would be the same as adding 8 pi over 4. We multiply top and bottom by 4, so we've got negative 7 pi over 4 plus 8 pi over 4. So that's going to be equivalent to 1 pi over 4. So I have a radius of 3 at an angle that's equivalent to 1 pi over 4. My angle here is pi over 4, and I'm going towards that angle with a radius of 1, 2, 3 units. So there's the point 3 comma pi over 4, which is equivalent to the point 3 comma negative 7 pi over 4. You could think about it as starting at the x-axis, and you can either rotate in the negative direction through an angle of 7 pi over 4, or you can just rotate in the positive direction through an angle of 1 pi over 4. And either way, you end up at the same spot. One last example, we have 6 comma negative 5 pi over 4. So I'm taking that negative angle and adding 2 pi to it, and then multiplying by 4 over 4 so that I get common denominators. That's the same as negative 5 pi over 4 plus 8 pi over 4. So this angle is going to be coterminal to a value of 3 pi over 4. So I'm going to be going 6 units away from the center in the direction or along the angle of 3 pi over 4. So there's my angle ray. And I'm going 1, 2, 3, 4, 5, 6 units from the center. That is point F. And like I said, the other thing that can happen is that you could have a negative radius. So if the angle is negative, that second value in the coordinate point is negative, then you have to add 2 pi to it until you get a positive angle. If the radius is negative, the radius represents the distance. So if radius is positive, then you're just going in the positive direction towards whatever angle you need. If the radius is negative, you're going to go in the opposite direction. So an example of this would be negative 3 comma pi. So my angle here is pi. Pi is right there on the circle. So if I were trying to plot the point 3 comma pi, then I would go 3 units towards pi. But since I'm trying to plot the point negative 3 comma pi, that means my radius is negative. I'm going to be going in the opposite direction. So instead of going along this ray towards the angle of pi, I'm going to go 1, 2, 3 units in the opposite direction. That would be the location of point G. H is a similar example. I've got negative 2 comma 19 pi over 12. So the angle 19 pi over 12 is right here. And if I were plotting 2 comma 19 pi over 12, I would go 2 units toward that angle. But since my radius is negative, I'm instead going to go in the opposite direction, 2 units away from the angle. That is the location of point H. Now points I and J, they are both negative. So if the angle is negative, we already learned what to do with that. You have to add 2 pi to it to get a positive angle. So negative 5 pi over 4 plus 2 pi is the same as negative 5 pi over 4 plus 4 pi over 4, 8 pi over 4. Multiplied by 2. So that's going to be equivalent to the point negative 7 comma 3 pi over 4. So if the angle is negative, deal with that first, add 2 pi to get a positive angle. Because now we can find this. 3 pi over 4 is an angle that's on my graph. It is right there. And now for the radius or the distance. My radius is negative 7. So instead of going 7 units towards that angle measure, I'm going to go 7 units in the opposite direction. 1, 2, 3, 4, 5, 6, and I end up down there. So up here would be the point 7 comma 3 pi over 4. And down here is the point negative 7 comma 3 pi over 4. One more example where we have both a negative radius and a negative angle is this last point labeled J. So again, when the angle is negative, take care of that first by adding 2 pi. So that would be negative 11 pi over 6 plus 12 pi over 6. So that would be equivalent to an angle of 1 pi over 6. So this point is equivalent to the point negative 2 comma 1 pi over 6. So my angle is 1 pi over 6, and since the radius is negative, I would go 2 units away from that angle point. So I would end up with point J being right there. So that is how to read and interpret and plot points on this polar coordinate grid. R represents the distance that you're going away from the origin. So that's going to be the first number in the ordered pair. And then theta, or the angle, represents what direction you're going to go in. So here is a collection of points for you to try on your own. Go ahead and pause the video, plot them out in your notes, and then hit play to see whether your points line up with mine. And here you can see these points that I've plotted. I've also color-coded them. The ones that people tend to have the most difficulty with are the ones with the negative angles. So double check the location of your points C, D, G, and H. Make sure that those look like you've plotted them in the same position as mine. And remember, anytime you have a negative angle, make sure that you are adding 2 pi to that so you can find a location that is a positive angle. So this is the basics of graphing in polar coordinate systems based on r and theta instead of x and y.